How can a mathematical model produce something that looks like a neuron firing? If we look at the biological neuron, you can see the illustrated one on the left. An action potential has a very characteristic shape: a rapid rise, a rapid fall, and even a brief hyperpolarization. On the right, you can see Leaky Integrate-and-Fire model. Notice something interesting about it. It doesn't reproduce that shape at all, and that is actually done intentionally. In this video, we are going to understand what Leaky Integrate-Fire model is doing, where its equations come from, and finally, implement that same model in Brian2. What are we trying to model? At a very simplified level, a neuron receives input from other neurons. These inputs change the electrical state of the cell, which we describe using its membrane potential. When a membrane potential reaches a certain level, a threshold, the neuron generates an action potential. The Leaky Integrate-and-Fire is based on three important ideas. You have input, you have loop, and you have some threshold. Input basically means spikes from other neurons. This pushes the membrane potential upward. But it cannot keep on going up and up. You cannot have it accumulate forever. So there's a leak factor. E of L, we call it resting potential or leak potential. When this membrane potential reaches a certain threshold, T of H, we say a spike has happened. So why doesn't the Leaky Integrate-and-Fire model reproduce the detailed shape of the action potential? Because the model is deliberately throwing away that detail. Look at this biological action potential. It's just an illustrative one. It doesn't copy everything. It's a very simplified version. We have resting potential. We have rapid depolarization, repolarization after hyperpolarization. But if you look at the Leaky Integrate-and-Fire model, it doesn't have any of those. It basically just have those three factors we just mentioned: input accumulation, a leak factor, a threshold, and after that threshold is reached, you have a reset. The Leaky Integrate-Fire model is primarily interested in the membrane dynamics between spikes and the timing of the spike event. This is why we don't need a very heavy CPU to simulate Leaky Integrate-and-Fire model. Now let's translate those three ideas into mathematics. We had three ideas. One was the leak term, the other was input, and the last one was something called threshold. The first term is the leak term. So we have V as potential, membrane potential, and EL is our leak potential. Suppose that our membrane potential is above resting potential. So we have something like this. We can write this in another way, like but notice the negative sign. So if I put the negative sign, this term forces the potential downward. So basically, wherever the potential is, if nothing else is happening, this term will continuously, slowly pull the potential towards E of L. The next term we have is the input. Ri, this term represents the effect of input current. If input is positive, which it normally is, the term pushes the membrane potential upward. You can clearly see the positive sign. Now, in this equation, you can clearly see two things. One is the leak term, the other is the input. That leaves this weird term here, tau of m. The idea is the membrane doesn't respond instantaneously. It behaves like a capacitor. The time constant tells us how quickly the membrane potential responds to its input. The tau m is time constant. If it's a small time constant, it will respond quickly. If it's a large time constant, it will respond relatively slowly. I will show you in our code later on this video how this works, but I have a small graph here. This is for tau of m when it's 20 milliseconds. Notice the horizontal axis here, how the spike rises slowly and reaches about, I think, nearly at 30 milliseconds at its peak, and then instantly falls down and move forward. So if I increase that tau of m to twice as much, say 40 milliseconds, you can see it here. Again, I'm sorry for the scale of the figures, but you can see on the horizontal axis, now it's moving upward all the way to nearly 60, I think 55 or something, at which point the our waveform reaches the peak position and then falls immediately. Again, I'll show you this in our coding at later point in this video. That leaves us with thresholds. Whenever membrane potential reaches a certain value, the threshold in this case, a spike event happens. After that, our membrane potential is reset to its original resting value. Notice that we haven't actually modeled the shape of the spike. The model simply says, once the membrane potential reaches threshold, emit a spike event. After that, membrane potential is reset. This is the computational abstraction that makes the Leaky Integrate-and-Fire model so simple. We look at membrane potential, it rises slowly, it reaches the threshold, spike happens, membrane potential is reset to the original value. So that's essentially our entire Leaky Integrate-and-Fire neuron models. We start with some membrane potential, we get some input, we accumulate that input, and we factor in our leak term. If our membrane potential crosses threshold, we spike and we reset. If it doesn't cross threshold, we just keep on accumulating more input. We keep on factoring in our more leak term till we do. Now let's implement exactly this model in code. I'm using Colab here. I'm using a framework called Brian2. We'll talk about Brian2 in later videos. So here I installed Brian2, imported everything from Brian2, and then we are setting our parameters. These are the same parameters we talked about previously. Basically, it covers our leak term, our input term, the threshold. So we have tau of m, time constant, membrane time constant, it's set to 20. We have our leak potential, our threshold value, what will happen after the spike, our input. We even have their units. I set these values so we can simulate the waveform as well as the spike. You can see here, if these values are set accordingly, we can have a specific value which might cross our threshold, which is what I was interested in because I wanted to show you spike happening. After this, this is our model, our Leaky Integrate-and-Fire model. This equation is a little bit different. It's a simple differential equation. This was the equation here I showed you. Basically, my time constant has been moved towards the right. Everything else is same. So you have this leak term, you have this input term, and everything is being divided by our time constant. And we have this particular thing in a unit volt. It's a characteristic of Brian2. We'll talk about that in a later video. So now that we have defined our model, we can start creating neurons. We have a function called neuron group from Brian2. We have to set some parameters for this. For example, number of neurons we want to create, the equation of the model. In this case, this is our This is our equation of leaky integrated environment. We said that here. What are the requirements for threshold? So if our membrane potential crosses this particular value, we have this set at minus 55 millivolts. That is when our threshold is crossed, right? And then what happened after crossing the threshold, our membrane potential is set to V reset, which is minus 70 millivolts. Then we have something else called refractory. Refractory period is the time when neuron is inactive. After neuron spikes, neuron enters a refractory period, a small time in which a neuron cannot spike again. Then we have a method. It's approximation method, I believe. We'll talk about this in Brian2 video. This is our initial state, how we're going to start the simulation. So our membrane potential will be at resting potential. I believe that's minus 70. Yes, that's minus 70 millivolts. So membrane potential start at minus 70 millivolts. Then we have something to record the values. So Brian2 provides us with state monitor and spike monitor. State monitor will record our membrane potential of this particular neuron group with only one neuron. So we will have membrane potential of that with respect to time, and this one will allow us to save the spikes. To run the simulation, we have this command from Brian2, and this is the duration for which we want the simulation to run. After running the simulation, we can extract values from our monitors here, like for example number of spikes, our time, voltage, and spike times. We can plot them in different ways. Let me run this for you. So first we install Brian2. This takes a little while. Import everything from Brian2. Set our parameters. Set our model. Create our neuron. Set its initial membrane potential. Set our state monitors. And run the simulation. This might take some time. So our neuron is getting some sort of input. Membrane potential is rising, maybe touching the threshold. A spike is happening. So this one will allow us to see how many spikes happen in this particular time slot. So we had 5 spikes, right? This way I can extract all the values. So we have time, voltage, and spike time. So let's plot this. So this is our membrane potential. So it starts from minus 70 millivolts, gradually rising, gradually rising, gradually rising. Touching the threshold, maybe there's a spike happening right now. Resetting to again minus 70 millivolts, again. So let's plot the spikes. So we have the spike. I think it's a little bit confusing. So let's plot them together. Bacteria. So this is our membrane potential, right? So it starts from minus 70 millivolts. It rises slowly, gradually, and it touches the threshold. The moment it touches the threshold, we have the spike event. It resets, again gradually rose all the way to here, threshold, spike, reset, again and again, and so on. So that is how you can implement Leaky Integrate-and-Fire neuron in Brian2. I will have separate video for Brian2, implementing different kind of neuron models and different kind of ways neuron can interact with each other. Another thing I wanted to mention in this video was about time constant. I mentioned it earlier. If you have a smaller time constant, this period here would be smaller. If you have a larger time constant, this period here will be larger. So we set tau of m to 20 milliseconds. Let's have a larger value, like say 14 milliseconds. Let's set the initial voltage again. Okay, before I run the simulation, there are two things you have to remember. One, number of spikes. For 20 milliseconds, you had 5 spikes. And another thing is this one. The first spike happened around 30 millisecond time off. So when you have time constant at 20 milliseconds, you get 5 spikes and a spike around 30 milliseconds. Right? So let's run this. See how many spikes we get. So our 5 spikes are reduced to 2. And let's see what happened to 30 milliseconds here. So before our waveform went to about 30 milliseconds and we got a spike. Now because of larger tau of m, it reaches almost near 60 milliseconds before it hits the threshold. So that will explain the time constant. It basically works like a capacitor. You have larger capacitance, it will take longer for the spike to happen. If you have smaller time constant, smaller capacitance, it will take smaller time for the same spike to happen. In this video, we built the Leaky Integrate-and-Fire neuron from its basic intuition, derived its mathematical formula, and implemented it in Brian2. On this side, you can see a biological illustration. It's a little bit complicated, but Leaky Integrate-and-Fire model simplifies everything. It just watches the membrane dynamics and when the spikes happen. So basically what we're remodeling, a simple input, a neuron does something, and we have a spike. What we look at mostly, we look at membrane potential. We basically had 3 basic ideas: input pushes, leak pulls, threshold trigger. The Leaky Integrate-and-Fire model had a particular equation. We talked about this. Time constant dv by dt is a leak term and input term. So you have leak term, an input term, and some sort of time constant. Then this is the next part of the Leaky Integrate-and-Fire neuron model. When the membrane potential crosses V threshold, we have a spike, and V is reset. This was the complete model. We start from V reset, we have some input, we accumulate the input, we have some leak factor, we check whether the membrane potential crossed the threshold or not. If yes, a spike event happens and we start over, or not, we go back to accumulating. We had a small implementation in Brian2. So this is how we set all our parameters. This is how we defined our model. The details of our model, like threshold and reset. In this case, we also set how many neurons we were creating. How are we recording the stuff from this model, how to run it, and then we basically had a couple of waveforms, spikes. In the next video, I am hoping to go deeper into Brian2 framework and trying different neuron models and different ways they interact.